We generally assume that massive buildings stay on the ground simply because they're heavy, but gravity is only half the story. Structures are under constant attack from invisible forces. Lateral wind shear pushes against the frame, while vertical uplift tries to pull it off the earth. All of that dynamic stress is funneled into a single high-pressure zone, the foundation connection. Engineers solve this by creating a hidden bridge. The anchor bolt connects a yielding material, like a steel column, to the unyielding mass of the concrete foundation. When this bridge fails, the structural loop is broken. A column that loses its grip on the foundation can no longer transfer its load to the earth, forcing the rest of the frame to compensate for a sudden point of localized instability. In the modern built environment, stability relies entirely on mastering the physics at this specific, microscopic point of contact. The first level of mastery involves securing heavy loads to concrete that has already cured and reached its full hardness. This requires a post-installed mechanical anchor. The most common tool for the job is the wedge anchor, which begins with a hole drilled precisely into the existing slab. Tightening the top nut draws a tapered steel wedge upward. This forces the metal sleeve outward, biting directly into the walls of the pre-drilled hole. This expansion generates intense mechanical friction, locking the fastener into the stone through sheer lateral pressure. This friction-based locking is why wedge anchors are the standard for industrial machinery floors, where equipment creates the kind of continuous vibration that would loosen traditional fasteners. Mechanical friction works for existing slabs, but the highest structural loads require a connection that is engineered before the concrete is even poured. As structural frameworks grow to the size of skyscrapers, the tension and shear forces become too great for a friction-only connection to manage. For these massive loads, engineers use cast-in-place anchors, massive L-bolts, J-bolts, or heavy threaded rods with steel plates welded to the base. These bolts are positioned using precise templates and suspended in the air within the formwork, waiting for the concrete to arrive. Once the concrete cures around these steel bends and plates, it creates a mechanical lock physically impossible to pull out without destroying the foundation itself. You see this scale in bridge piers and primary building columns, where the anchor must resist the immense uplift forces generated by wind or seismic activity. By fusing the steel and the stone at the moment of inception, the building and the foundation function as a single continuous unit. The ultimate challenge arrives when anchors must perform in compromised environments, where the concrete is already cracked or the air is thick with corrosive salt. In these scenarios, mechanical expansion might shatter a weakened concrete edge. The solution is the chemical anchor. Instead of using pressure, a two-part epoxy resin is injected into the hole. It seeps into the microscopic pores and microcracks of the concrete, curing into a solid mass that bonds the steel rod to the stone on a molecular level. To survive for decades in these harsh conditions, the bolts themselves are forged from stainless steel 316, or heavy-duty galvanized alloys, to prevent the chemical degradation that would otherwise eat through standard steel. This represents the peak of anchoring mastery, protecting the connection not just from physical force, but from the slow decay of the elements. Every iconic structure we've built is a testament to these three levels of anchoring: friction, fusion, and chemistry. On the Golden Gate Bridge, anchoring systems secure the suspension cables that hold the massive weight of the deck against the forces of the Pacific. At the Burj Khalifa, clusters of high-strength bolts keep the world's tallest columns tethered to the bedrock, despite the relentless desert winds. And inside our power plants, specialized anchors endure the violent, constant rotation of turbines that generate the energy for our cities. The stability of these landmarks rely on the successful transfer of energy through the load path, terminating at the anchors that bind the steel to the earth. Our ability to build taller and span further is the result of solving the transition between yielding steel and unyielding stone, ensuring that even under extreme stress, the connection remains the strongest part of